So, we start the second module of this course. This week we will be mainly concerned with the properties of derivative. So, in the last lecture we have seen that given a linear math operators from Rn to Rm, how it is to be realized as a matrix of M cross N. So, we continue with that suppose I have F again U in Rn to Rm and x naught in U, F is differentiable according to our definition at x naught. So, how to compute matrix of this derivative? Remember, derivative is a linear map from Rn to Rm. Okay, we follow the same pattern as we did in the case of a linear map from Rn to Rm. We observe the matrix will be a M cross N matrix. What will be the first column? So, if I fix basis, fix canonical basis, canonical basis E1 n E n n, this is for Rn, and E1 m E1 E n m, this is for Rm, correct. With that, from the previous calculation we know the first column of df of matrix of dfx naught, this will be dfx naught acting at E1 n. If you recall the calculation, this is what we have, but we have already proved something that E1 n is a direction in Rn, right. For instance, if I have in R3, this is a direction E1 1, this is E2, E1 3, E2 3, E3 3, E2 3. So, this is the direction E1 3, and you know this fellow will be equal to the directional derivative with in the direction E n at the point x naught. Remember, we have proved it in the last lecture. So, what is this? Now, I apply the definition. This is limit h going to 0 h f of x naught plus h E1 n minus f of x naught. We denote it by some special notation. So, this is a special notation for this particular direction. If I fix a canonical basis, we make a special notation for this limit and we call it del f del x1 at the point x naught. Now, f is from Rn to Rm. So, I know f can be written as f1, f2, fm, where each fi or fk is from u to r. So, f is actually this vector. So, maybe I should write in the column vector. So, if I write del f del x 1 at x naught, this will be a column vector del f 1 del x 1 at x naught, del f 2 del x 1 at x naught, and so on up to del f m del x 1 at x naught. So, I got the first column of the matrix of d f x naught. Now, there is nothing special about first column. If I change 1 to any variable x k, then I will get the kth column. So, what I mean here that jth column, let us say, of matrix of d f x naught will be d f e j n at x naught, and according to this prescription I will write here del f del x j, which is del f 1 del x j at x naught, del f 2 del x j at x naught, del f m del x j at x naught. Now, I got all the columns, and now put j equal to 1 to n, I got all the columns. So, finally, I get matrix of d f x naught is equal to first column second column and finally, the nth column this is I equal to 1 to m, j equal to 1 to n. So, this is m cross n matrix, which is the matrix of d f x naught. And again, if you see, if you in books or notes, they have again special notation for this one. Don't usually the book do not write in this form matrix d f x naught, they write it as j f at x naught, and it has a name, is called Jacobian of f at x naught. So, look at it very carefully, and then I want to make a comment. So, what we have done here, we want to compute the matrix of d f x naught, assuming f is differentiable. If is differentiable, then this will be, I look at I wanted to first find out the first column or kth column, I evaluated at E k n, and I know by previous theorem that this is directional derivative in the direction of E k n, and I calculate that, put the columns together, I get it. But there is a point here. Thing is that suppose I get any function, if I give you any function f from R n to R m or some subset of R n to R m. You know, in the first example, one of the examples, the directional derivatives in all direction may exist, but still the function may not be differentiable in our sense, because it may not fail to be continuous. So, given any function f, maybe this all these fellows exist, del f I del x j, all of them exist, but f may still fail to be differentiable. So, given any f, actually after computing this I have to check that this is the derivative, that is, it satisfies the definition. I explain it through an example. Let us take a very simple example. Let us say f is from entire R 2 to R 3 and f of x y, two variable. Let us say, let us take something simple. Okay. Then according to prescription, this prescription, first I will write as f equal to f 1, f 2, f 3, where f 1 is from R 2 to R equal to x, f 2 x y is y, f 3 x y is equal to x square plus y square. Correct. Now I know, so I am checking at a point x naught equal to x naught y naught, some arbitrary point. So candidate, I write candidate because I still do not know. So let me write it. So I not let me say it. I still do not know, given arbitrary point at x naught y naught, if it is differentiable or not, because I have not checked the definition. But if it is differentiable, again if it is differentiable, then candidate for d f x naught is, from this formula, is del f 1 del x, then del f 2 del y, and then del f 2 del x, del f 3 del x, then del f 1 del y, del f 2 del y, del f 3 del y. Correct? This will be a I equal to 1 to 3, j equal to 1 to 2, because it is R 2 to R 3. So let us calculate the entries. Del f 1 del x, which is how much is that? This is simply 1, and del f 1 del y, this is 0, del f 2 del x, this is f 2 is x y, del x is 0, del f 2 del y, this is 1, del f 3 del x, this is equal to 2x, and del f 3 del y is equal to 2y. So again, candidate for df at x naught is how much? 1 0 0 1 2 x naught to y naught. I have to evaluate it at x naught y naught. But this is only candidate. Now I have to verify definition. Verify through the definition. That is, I have to put h e x naught h equal to f of x naught plus h minus f of x naught minus. So this is according to our notation j f at x naught y naught, j f x naught acting at h, and to show E x naught h goes to 0 as h goes to 0. Well, let us check. Let h is in R2, h1, h2. So, norm of h is h2 square. Let us calculate this fellow. F of x naught plus h1 y naught plus h2 minus f of x naught y naught minus j f x naught at h is h1 h2, which is equal to, if I write in column form, what is it, x naught plus h, y naught plus h, x naught plus h whole square plus y naught plus h whole square minus x naught y naught x naught square y naught square minus j f x naught, this matrix acting at h1 h2 h1 h2, this matrix acting at h1 h2, you can easily compute, that will be how much, h1 then h2 and then 2 x naught h1 plus 2 y naught h2. Okay. Continue the calculation here. This implies equal to how much? This will get cancelled, second column will get cancelled, third column remains. So, 0 0 h1 square plus h2 square. So, E x naught h is simply 0 0 h1 square divided by h2 square divided by norm of h, but norm of h is this, which is 0 0 root over, of course, this goes to 0 as h goes to 0, because h goes to 0 implies norm of h goes to 0, this is precisely this quantity. So, after this calculation we can now surely declare for any x naught y naught in R2, f is differentiable at x naught y naught and derivative at the Jacobian matrix is 1 0 0 1 2 x naught 2 1 naught. So, you see there is some bit of work done, work has to be done. Even if you calculate this matrix J f x naught J of Jacobian matrix, you have to actually check that this thing, this candidate is actually the derivative. It may not be, we have examples. Let us look at another example, I will let you to do it, very easy example. F is from, let us say, R n to R, so real valued, given by f of x, let us say x equal to x1 x2 xn equal to just norm of x square, which is by definition is x1 square x2 square xn square. Now, there is m equal to 1, so there is only one f. So, Jacobian matrix will be, according to our prescription, this will be a matrix 1 cross n matrix, that is a row vector. And what is that row vector will be? This is del f del x1 del f del x2 del f del xn evaluated at the point x naught. Again you will see in the book people do not write g of x naught for function from Rn to R, one usually write it as grad f at x naught. So, this is again candidate for df at x naught, and we have to check that h e x naught h equal to f x naught plus h minus f of x naught minus grad f x naught at h, and I have to check E x naught h goes to 0 as h goes to 0. I leave the verification on you. So, write down everything and check it actually works, and with one word I will finish the lecture today. That is, you can easily see this. Okay, first of all, what is this fellow? A 1 cross n matrix acting on a 1 n cross 1 vector, that is actually inner product. How does this vector acts on H? So, if H is H1, H2, Hn, then this is actually del f del x1 all the way up to del f del xn dot H1, H2, Hn, which is summation Hi del f del xi I equal to 1 to n. So, you use that, and of course, you can calculate the del f at x naught is simply del f x1 is 2x1, this is 2x2, 2xn evaluated at x equal to x1, x2, xn. Okay. So, do the exercise and we will continue from here.